What if the universe is expanding faster than light itself? Think about that for a second. Not just stars or galaxies moving apart, but the very fabric of space stretching faster than anything we thought possible. It sounds like science fiction, but it's one of the most mind-bending questions keeping cosmologists up at night. And here's the thing, this isn't just a wild idea. It's part of a much bigger mystery, one that challenges everything we think we know about the cosmos. From the moment Edwin Hubble first noticed galaxies speeding away from each other, we've been grappling with the reality that the universe isn't static. It's alive, growing, and full of secrets we're only beginning to uncover. Picture the universe like an inflating balloon, with galaxies as dots on its surface. As the balloon expands, those dots move farther apart. But what if the balloon isn't just inflating? What if it's doing so in ways that defy all our expectations? Dark energy, mysterious forces, even the possibility of hidden dimensions, these are just a few of the puzzles scientists are racing to solve, and despite decades of research, we've only scratched the surface. There are at least 25 colossal questions about cosmic expansion that still leave experts stumped. Questions like, why is the expansion speeding up? What's really driving it, and could there be parts of the universe already moving beyond our reach, lost forever to the void? This isn't just about distant stars or abstract physics. It's about the very nature of reality, our place in a cosmos that's far stranger and more wondrous than we ever imagined, and that's exactly what we're diving into today. We'll explore the biggest unsolved mysteries of the universe's expansion, from the forces we can't see to the edge of what we think is knowable. By the end, you'll see why these questions aren't just academic. They're the keys to unlocking the ultimate story of existence itself. So buckle up, we're about to take a journey into the deepest unknowns of space, time, and the forces shaping everything we see and everything we don't. One of the most baffling puzzles in modern cosmology is why the universe seems to be expanding faster than our best theories predict. For decades, scientists have measured the rate of cosmic expansion using two main methods: observing nearby galaxies and analyzing the faint glow of the cosmic microwave background, the afterglow of the Big Bang. Here's the catch, these two approaches keep giving us different answers. It's like using two separate speedometers to measure a car's velocity, only for one to say you're going 60 miles per hour, while the other insists it's 70. This mismatch is called the Hubble tension, and it's throwing our understanding of the cosmos into question. So what's causing this discrepancy? One possibility is that we're missing something fundamental in our measurements. Maybe interstellar dust is subtly distorting our view of distant galaxies, or perhaps there's an overlooked error in how we interpret the cosmic microwave background. But the more thrilling and unsettling idea is that our theories themselves are incomplete. Could dark energy, the mysterious force accelerating the universe's expansion, be changing over time, or is there an entirely new force or particle at play, something beyond the known laws of physics? Some scientists speculate that dark energy isn't constant, but instead grows stronger as the universe expands, pushing galaxies apart at an ever-increasing rate. Others wonder if we're seeing the effects of extra dimensions, hidden layers of reality influencing cosmic expansion in ways we can't yet detect. Then there's the radical notion that gravity itself behaves differently on the largest scales, meaning Einstein's equations might need revising. Each of these ideas has profound implications, not just for the fate of the universe, but for the very laws that govern it. The Hubble tension isn't just a technical disagreement, it's a signpost pointing to gaps in our knowledge. If one of these bold theories proves correct, it could rewrite cosmology as we know it. Imagine discovering that dark energy evolves, or that gravity weakens over cosmic distances. These aren't minor tweaks, they'd revolutionize our understanding of space, time, and everything in between. Yet for now, the mystery stands. a tantalizing reminder that the universe still holds secrets we've only begun to uncover. If the expansion of the universe were a cosmic tug-of-war, dark energy would be the invisible hand pulling the rope harder than anyone expected. We've known about its existence since the late 1990s, when astronomers studying distant supernova made a startling discovery. Instead of slowing down due to gravity, the universe's expansion was speeding up. It was as if someone had flipped a switch, unleashing a force so powerful it counteracted the pull of every galaxy, star, and black hole in existence. And just like that, dark energy became one of the greatest mysteries in modern physics. The leading explanation ties back to Einstein's cosmological constant, a term he originally added to his equations to keep the universe static, later calling it his greatest blunder when evidence pointed to an expanding cosmos. But in a twist of irony, that same constant might describe dark energy, a uniform energy woven into space itself, pushing galaxies apart. Here's the catch: calculations suggest this energy should be unimaginably stronger than what we observe. The discrepancy is staggering, off by a factor of 1 followed by 120 zeros. That's not a rounding error, it's a screaming red flag that something's missing. This gap has sparked wilder theories, like quintessence, a dynamic energy field that could vary over time or space, unlike the static cosmological constant. Imagine dark energy as a cosmic thermostat, subtly adjusting its strength as the universe evolves. Then there's vacuum energy, the idea that empty space isn't truly empty but seething with particles flickering in and out of existence. But again, the math doesn't line up. Even quantum physics can't explain why dark energy is so faint compared to theoretical predictions. The real shocker: dark energy doesn't just defy explanation, it challenges Einstein's theory of gravity itself. General relativity has passed every test for over a century, from bending starlight to predicting black holes. Yet if dark energy behaves in ways Einstein's equations can't account for, we might need a radical rewrite of how gravity works on cosmic scales. Some theorists propose hidden dimensions or exotic particles altering gravity's pull across vast distances. Others wonder if our universe is just one bubble in an infinite multiverse, each with its own rules. What makes dark energy so thrilling and frustrating is that it's not just about filling a gap in our equations. It's about understanding the fate of everything. Will expansion eventually tear galaxies, stars, and even atoms apart, or could dark energy fade, allowing gravity to crunch the cosmos back into a singularity? Right now, every answer leads to deeper questions, reminding us that the universe still holds cards it hasn't shown. If the universe were a perfectly smooth balloon inflating at a steady rate, every galaxy should drift apart in predictable harmony. But telescopes are revealing something far messier, a cosmic tapestry where expansion doesn't play by uniform rules. Take the so-called dipole mystery, vast regions of space where galaxies appear to recede faster in one direction than another, as if the universe itself is lopsided. It's like blowing up a balloon only to notice one side stretches more than the other, a wrinkle that defies our simplest models of cosmic growth. These anomalies aren't just quirks, they're cracks in the foundation of modern cosmology. Galaxy cluster surveys, like those mapping thousands of galaxies across billions of light-years, keep stumbling upon cosmic inhomogeneities, colossal bubbles of space where matter clumps unevenly, warping the local rate of expansion. Imagine pouring syrup onto a waffle. Some pockets stay thin while others pool thickly. Now picture that syrup as spacetime itself, with gravity's grip stronger in dense regions, subtly slowing expansion there while emptier zones stretch faster. Could these variations mean our average expansion rate is just an illusion, masking a far more complex reality? Some theorists argue these irregularities are cosmic ghosts, echoes of the universe's fiery birth, when quantum fluctuations froze into the fabric of space, seeding today's uneven expansion. Others propose darker explanations, like rogue patches of dark energy flaring up in specific regions, or even gravitational ripples from collisions with unseen parallel universes. The most unsettling possibility, that we're not just misreading the data, we might be fundamentally wrong about how expansion works. For decades, scientists assumed the cosmos was isotropic, meaning it looks the same in all directions on large scales. But if that's not true, it would force a reckoning with Einstein's principle of cosmic humility, the idea that we shouldn't assume our corner of the universe is special. What if our patch is atypically smooth, and the broader cosmos is a chaotic mosaic of expansion speeds? Future telescopes, like the European Space Agency's Euclid mission, aim to settle the debate by creating ultra-precise 3D maps of billions of galaxies. Until then, the dipole mystery remains a tantalizing clue that the universe might not just be expanding, it could be unraveling in ways we've barely begun to imagine. Could the universe end not with a slow fade, but with a violent, all-consuming tear? That's the spine-chilling premise of the Big Rip, a scenario where dark energy doesn't just push galaxies apart, but grows so powerful, it shreds the very fabric of reality. Picture this: first, distant galaxies vanish beyond our cosmic horizon, ripped away by runaway expansion. Then, gravity loses its grip, tearing apart our own Milky Way. Stars, planets, even atoms themselves are pulled apart, as the force of expansion overcomes every fundamental force holding matter together. It's not just an ending, it's a complete unraveling of existence. This nightmare scenario hinges on a critical question: does dark energy intensify over time? Right now, it appears constant, but if it's something more volatile, like the theoretical phantom energy, its strength could grow exponentially. Think of it like stretching a rubber band. At first it resists, but if you keep pulling, it eventually snaps. In cosmic terms, that snap would mean even the bonds between quarks, the building blocks of protons and neutrons, are no match for dark energy's grip. The universe wouldn't just expand, it would disintegrate, but the Big Rip isn't the only possible finale. For decades, scientists debated between two other fates: the Big Crunch and heat death. The crunch imagines gravity eventually reversing expansion, collapsing the universe back into a singularity, a mirror image of the Big Bang. Heat death, on the other hand, paints a quieter but equally bleak picture. Expansion continues until all stars burn out, black holes evaporate, and the cosmos becomes a vast, cold wasteland of near-zero energy. These outcomes hinge on the universe's critical density, the delicate balance between expansion and gravity's pull. Here's where it gets fascinating. Measurements suggest we're right on the knife's edge. If the density of matter and energy were slightly higher, gravity might win, leading to a crunch. Slightly lower, and dark energy could dominate, dooming us to eternal expansion, or worse, a rip. Yet current data points to an eerie middle ground, where expansion accelerates just enough to avoid a crunch, but not so violently that atoms are torn apart. At least for now, the scariest part: we might not have to wait billions of years for clues. Some models suggest subtle changes in dark energy's behavior could be detectable within decades. Telescopes like the Vera Rubin Observatory could spot signs of phantom energy's influence on distant supernova, while gravitational wave detectors might catch whispers of spacetime itself straining under expansion's grip. The Big Rip remains speculative, but it's a stark reminder that the universe's fate isn't just a philosophical question, it's a race against time to decode the forces that could one day pull everything apart. The universe didn't just expand, it exploded into being in a fraction of a second, stretching from smaller than an atom to cosmic scales faster than light itself. This mind-bending moment, called cosmic inflation, happened just moments after the Big Bang and set the stage for everything that followed. But here's the puzzle: how does that unimaginably rapid burst of growth connect to the slower, steadier expansion we see today, or the sudden acceleration driven by dark energy? It's like trying to piece together a movie where the first scene is a blur of action, the middle drags on, and the ending speeds up again without explanation. Inflation theory, first proposed in the 1980s, solves several cosmic mysteries at once. It explains why the universe looks so smooth on large scales, because space stretched so quickly that any wrinkles got ironed out, and why distant regions have the same temperature despite being too far apart to ever interact. But inflation also made a bold prediction. It should have created ripples in spacetime itself, gravitational waves imprinted on the cosmic microwave background. Decades of searching, however, have come up empty. The most sensitive experiments like the BICEP and Planck telescopes found no trace of these primordial waves, leaving scientists scrambling to understand why. Some theorists argue the waves might simply be fainter than expected, buried under cosmic noise. Others wonder if inflation didn't happen exactly as we thought. Perhaps it unfolded in multiple phases, or involved exotic physics beyond our current models. The Planck satellites' detailed maps of the microwave background added another twist. While they confirmed many predictions of inflation, they also revealed subtle anomalies, like unexpected variations in the universe's curvature. These quirks suggest inflation might not have been uniform, with some regions stretching faster or longer than others. Then there's the elephant in the room, dark energy. If inflation was the universe's first acceleration and dark energy is its latest, are they two versions of the same phenomenon? Both involve space itself expanding at breathtaking scales, both defy conventional physics, and both remain deeply mysterious. Some speculate dark energy could be a relic of inflation, a dormant force that reawakened as the universe grew sparse. Others propose an even stranger idea, that we're living through a second inflationary phase, one so slow we barely notice it until now. The stakes couldn't be higher. If inflation and dark energy are linked, it would mean the universe operates on a grand cycle of speeding up and slowing down, with forces we've yet to name shaping its destiny. Or perhaps inflation was a one-time event, and dark energy is an entirely different beast. Either way, the silence of those missing gravitational waves is deafening, a clue that the early universe might hold secrets even our boldest theories haven't imagined. Until we crack this cosmic code, the story of how inflation connects to today's expansion remains one of the greatest unsolved chapters in the history of everything. What if the forces shaping our universe aren't confined to the three dimensions we experience every day? String theory, one of the most ambitious frameworks in physics, suggests there could be as many as 10 or 11 dimensions, tiny, curled-up spaces hidden from our perception. These extra dimensions aren't just theoretical curiosities, they might hold the key to why the universe is expanding the way it is. Imagine space as a loaf of bread, with our visible universe just a single slice. Other slices, parallel brains in higher dimensional space, could be influencing our reality in ways we're only beginning to grasp. One provocative idea is that dark energy, the mysterious force accelerating cosmic expansion, might actually be gravity leaking into these extra dimensions. In some models, gravity is weaker than other forces because it isn't confined to our three-dimensional brain. It spills into the higher dimensional bulk, diluting its strength. This leakage could explain why dark energy's effects seem so faint compared to theoretical predictions. Think of it like water seeping through cracks in a dam. What we perceive as a mysterious push outward might actually be gravity slipping away into unseen realms. Then there's the question of whether these extra dimensions could warp expansion itself. If our brain is colliding or interacting with others in higher dimensional space, it might create ripples that stretch or distort spacetime in ways we interpret as accelerated expansion. Picture two soap bubbles drifting close together. Their surfaces could subtly repel or attract each other, altering how each bubble expands. Some theorists even speculate that what we call dark energy is just the fingerprint of a neighboring brain's gravity gently tugging on ours from another dimension. The challenge proving any of this Extra dimensions, if they exist, would be vanishingly small, far beyond the reach of current particle colliders, but there's hope on the horizon. Subtle anomalies in gravitational waves, or deviations in the behavior of distant cosmic structures, might one day betray the presence of higher dimensions. The Euclid Space Telescope, for example, could uncover patterns in galaxy distributions that hint at gravity behaving oddly across vast distances, a potential sign of dimensional leakage. String theory and brane cosmology offer a breathtaking vision. Our universe might be just one layer in a vastly richer multidimensional reality. While these ideas remain speculative, they remind us that the cosmos could be far stranger and more interconnected than we ever imagined. If even a fraction of these theories hold water, it wouldn't just solve the mystery of dark energy, it would rewrite our very understanding of existence. Until then, the hunt for higher dimensions continues, a tantalizing frontier where the fabric of space itself might be hiding its deepest secrets. Stretching between galaxies and superclusters, the cosmic web is anything but empty. Vast voids, some spanning hundreds of millions of light-years, sit like gaping holes in the fabric of space, bordered by thread-like filaments where galaxies cluster in dense, glowing strands. This intricate structure, more sponge than uniform expanse, should, in theory, match the predictions of our best cosmological simulations, but when scientists compare these cosmic maps to the lambda CDM model, the reigning framework of the universe's evolution, something doesn't add up. The voids are too big, the superclusters are too clustered, and this mismatch might be twisting the very rate of expansion itself. Take the Boötes void, a cavern of near-nothingness so immense you could fit 60 Milky Ways end-to-end across its emptiness. Regions like this aren't just curiosities, they're cosmic regulators. With so little matter inside, gravity's pull is weaker, allowing space within voids to expand faster than in denser regions. It's as if the universe has built-in speed zones, with emptiness stretching aggressively while galaxy-rich filaments resist. The problem: lambda CDM simulations predict voids should be smaller and more evenly scattered. Instead, we see sprawling deserts of space alongside crowded galactic metropolises, a distribution so uneven it throws off calculations of the universe's average expansion rate. This isn't just a mapping error. The discrepancy hints that dark energy or gravity might behave differently in these extreme environments. Imagine pouring water over two patches of soil, one compacted, one loose. The water flows at different rates, just like expansion might warp in response to local density. Some theorists suggest voids amplify dark energy's effects, creating pockets where space stretches like overworked taffy. Others propose that gravity itself weakens in these barren regions, a deviation from Einstein's equations that could rewrite how we model cosmic growth. Then there's the KBC void, a controversial structure 7 times wider than expected, where our own Milky Way sits near the edge. If confirmed, it would mean we're inside a local bubble of underdensity, skewing our measurements of universal expansion like a ship drifting in a calm bay while storms rage beyond the horizon. This Hubble bubble effect could partially explain the tension between local and distant measurements of expansion, a reminder that our cosmic address might distort our view of the whole. Upcoming telescopes like JWST and the Square Kilometre Array aim to settle the debate by charting voids and filaments with unprecedented precision. Will they reveal hidden laws of physics governing these empty realms, or will the voids grow even more mysterious, forcing us to rethink the cosmic playbook? Either way, these gaping absences aren't just empty space, they're alive with clues, silently reshaping our understanding of how the universe grows. For over a century, cosmology has operated on one foundational belief, that on the largest scales, the universe looks roughly the same in every direction. Known as the cosmological principle, this idea suggests matter and energy are evenly distributed when you zoom out far enough, making no region fundamentally special. It's the reason we can extrapolate cosmic expansion rates from our local observations and assume they apply universally, but what if this bedrock assumption is wrong? Mounting evidence suggests the universe might not be as uniform as we thought, with peculiar structures and anomalies that defy the principle's predictions. Take the so-called axis of evil, the bizarre pattern in the cosmic microwave background where temperature fluctuations appear oddly aligned along a specific plane of the sky. Instead of random variations, these hot and cold spots seem to whisper of a preferred direction, almost as if the universe has a subtle tilt. It's like spinning a globe and noticing all the continents somehow line up along one invisible seam. Even stranger, this axis roughly aligns with the plane of our solar system, raising uncomfortable questions. Is this a real cosmological feature, or are we somehow contaminating the data with our own vantage point? Then there's the Great Attractor, a gravitational anomaly pulling thousands of galaxies, including our own Milky Way, toward a single point in space with the force of tens of thousands of Milky Ways. We can't directly see what's causing it, the region lies obscured by our galaxy's dusty disk, but its existence challenges the notion of smooth, even distribution. If matter were truly homogeneous, such colossal overdensities shouldn't exist. Similarly, the Hercules Corona Borealis Great Wall, a filament of galaxies stretching over 10 billion light-years, dwarfs even the largest structures predicted by standard cosmology. Finding a cosmic wall that big is like expecting scattered pebbles on a beach, and instead discovering a mountain range. Critics argue these anomalies might just be statistical flukes, cosmic illusions magnified by our limited perspective. After all, we're observing the universe from a single point in space and time, like trying to map an entire forest by studying one tree, but supporters of inhomogeneity point to deeper implications. If the cosmological principle fails, it could mean dark energy's effects vary across space, or that Einstein's equations break down at scales larger than we've tested. Some theorists propose radical alternatives, like fractal cosmology, the idea that matter clusters in self-similar patterns no matter how far you zoom out, violating large-scale homogeneity entirely. The stakes are high. If the universe isn't uniform, our measurements of its expansion, age, and fate could be fundamentally skewed. Imagine trying to calculate the average speed of cars on a highway, but unknowingly only clocking vehicles in the fast lane. Your results would be wildly off. Similarly, if we're in a local bubble of atypical density, our cosmic yardsticks might be misleading. Upcoming surveys like the Euclid mission aim to settle the debate by mapping billions of galaxies in unprecedented detail, searching for hidden patterns or biases in their distribution. What makes this question so thrilling is its philosophical weight. The cosmological principle isn't just a scientific tool, it's a statement about our place in the cosmos. If it holds, we're in an unremarkable corner of a vast, balanced universe. If it cracks, we might be part of something far stranger, a lopsided, textured reality where no two regions play by the same rules. The answer won't just reshape textbooks, it could redefine how we see existence itself. Empty space isn't truly empty, not by a long shot. According to quantum mechanics, the vacuum of space seethes with energy, a swirling ocean of particles flickering in and out of existence so fast we can never catch them in the act. These fleeting disturbances, known as quantum fluctuations, are more than just theoretical oddities. They might hold the key to one of cosmology's greatest embarrassments, the staggering mismatch between predicted and observed dark energy. Here's the problem in a nutshell. When you calculate how much energy these quantum fluctuations should contribute to the vacuum, the number is astronomically high, around 1 followed by 120 zeros times stronger than what we actually measure. To put that in perspective, it's like expecting a tsunami and instead finding a single ripple in a teacup. This discrepancy isn't just a minor hiccup, it's been called the worst theoretical prediction in the history of physics. So where does all that missing energy go? One possibility is that we're fundamentally misunderstanding how quantum mechanics interacts with gravity. General relativity and quantum theory, the twin pillars of modern physics, famously refuse to play nice when it comes to the vacuum, while quantum mechanics treats empty space as a frenetic dance of virtual particles. Relativity sees it as a smooth, curved stage. When you try to merge these views, the math explodes into nonsense. Some theorists argue that unknown symmetries or cancellations might be at work, silently negating most of that energy before it can influence cosmic expansion. Others speculate that gravity itself might act differently at quantum scales, effectively shielding us from the vacuum's full fury. Then there's the holographic principle, a radical idea suggesting our three-dimensional universe might be a projection of information stored on a two-dimensional boundary. In this scenario, the true degrees of freedom and thus the vacuum energy are far fewer than standard quantum calculations suggest. Picture a movie screen. No matter how detailed the image, it's still just light projected from flat surface. If spacetime works similarly, the vacuum's energy could be dramatically diluted, explaining why dark energy is so faint, but the most tantalizing clue might come from an unexpected source: black holes. Studies suggest that the entropy of a black hole, a measure of its hidden information, scales with its surface area, not its volume. This hints that the universe might fundamentally limit how much energy can cram into any given space, effectively capping vacuum energy far below theoretical predictions. If true, it would mean dark energy isn't missing at all, we've just been calculating it wrong all along. The mystery of quantum fluctuations and expansion isn't just academic. If these tiny invisible ripples really do shape the cosmos, they could reveal deeper laws weaving together quantum mechanics and gravity. Until then, the vacuum silence remains one of science's loudest unanswered questions, a whisper from the void that might someday rewrite physics itself. For decades, redshift, the stretching of light toward the red end of the spectrum, has been our primary evidence that the universe is expanding. When we observe distant galaxies, their light appears redder than it should, and the farther away they are, the more extreme this shift becomes. The standard explanation is straightforward. As space itself expands, it stretches the wavelengths of light traveling through it, much like ink dots on an inflating balloon spreading apart. But what if we've been reading the cosmic clues wrong? A small but persistent group of researchers argues that redshift might not always mean what we think it does. Take the tired light hypothesis, an alternative idea dating back to the 1920s. Instead of space expanding, this theory suggests light loses energy as it travels vast distances, gradually reddening as it interacts with the fabric of space itself. Picture a marathon runner slowing down over miles, not because the track is stretching, but because each step drains a little more stamina. Proponents point out that tired light could explain redshift without requiring an expanding universe. But there's a catch: losing energy this way should also blur distant galaxies, scattering their light like fog obscuring a street lamp. Yet when we look at far-off galaxies, their images remain crisp and clear, a detail that's hard to square with tired light's predictions. Then there's gravitational redshift, a well-documented effect where light climbing out of a strong gravitational field, like near a black hole, shifts toward the red. Could some of the cosmic redshift we measure actually be gravity's fingerprint? It's possible, but the math doesn't add up. The redshifts we observe are too uniform, too precisely correlated with distance, to be explained by random gravitational boosts alone. If gravity were the main driver, we'd expect a chaotic patchwork of shifts, not the smooth gradient we actually see. Mainstream cosmology dismisses these alternatives for good reason. The expansion model doesn't just explain redshift, it ties neatly into a web of other evidence, from the cosmic microwave background to the abundance of light elements forged in the Big Bang. Tired light and gravitational redshift, on the other hand, struggle to account for these broader observations without introducing convoluted fixes. yet the debate isn't entirely settled. Some researchers continue to explore hybrid models, like light interacting with exotic quantum fields or dark matter, that might blend aspects of expansion with other redshift mechanisms. What makes this question so intriguing isn't just the science, it's the reminder that even our most trusted cosmic yardsticks deserve scrutiny. Redshift has guided our understanding of the universe for a century, but science thrives on questioning the obvious. Whether it holds up or not, the conversation pushes us to dig deeper, to test our assumptions, and to stay humble in the face of the cosmos mysteries. After all, if history has taught us anything, it's that the universe loves to surprise us. For most of cosmic history, the universe behaved exactly as you'd expect after the explosive rush of the Big Bang. Gravity took the wheel, gradually slowing the expansion down like a car coasting to a stop. Galaxies pulled on one another, dark matter exerted its invisible grip, and everything seemed headed for a predictable, gradual unfolding. Then, about 5 billion years ago, something bizarre happened. Without warning, the universe slammed its foot on the accelerator. Dark energy, or something like it, overpowered gravity's drag, sending galaxies hurtling apart at ever-increasing speeds. This flip from deceleration to acceleration wasn't just subtle, it was a cosmic U-turn, one that still leaves scientists scrambling for answers. To understand this transition, imagine throwing a ball straight up. Normally, gravity slows it until it stalls and falls back down, but what if, at the peak of its arc, the ball suddenly shot upward faster than before? That's the equivalent of what happened to the universe. For billions of years, expansion slowed, then, against all intuition, it reversed course, the smoking gun. Baryon acoustic oscillations, faint ripples frozen in the cosmos from its infancy, these primordial sound waves left a telltale fingerprint in how galaxies cluster, acting as a cosmic ruler. By measuring these patterns at different distances and thus different eras, scientists can reconstruct how expansion changed over time. The data reveals a clear inflection point, a moment when the universe's brakes gave way to an unseen throttle. What triggered this cosmic jerk? The leading suspect is dark energy's density. While matter and radiation dilute as the universe expands, dark energy appears to maintain a constant density, meaning its influence grows relative to everything else. Picture a crowded party where guests slowly leave. The host's voice becomes easier to hear as the room empties. Similarly, as galaxies spread out, dark energy's push against gravity becomes dominant. But here's the twist: some models suggest dark energy might not be constant. Quintessence theories propose it could evolve, weakening or strengthening over time. If that's true, the acceleration we see now might just be a phase in a longer, more complex dance. The transition also raises a profound question: was it truly sudden, or have we missed subtle clues from earlier epochs? Observational gaps in our cosmic timeline, particularly during the universe's dark ages, before stars ignited, mean we might be piecing together an incomplete puzzle. Future telescopes like NASA Roman Space Telescope aim to probe this era with unprecedented precision, hunting for hints of dark energy's awakening. Until then, that mysterious flip from slowing down to speeding up remains one of cosmology's most puzzling plot twists, a reminder that the universe's story is far from straightforward. Dark energy and dark matter, two of the most enigmatic ingredients in the cosmic recipe, might not be as separate as we think. For years, scientists treated them like strangers in the night, dark matter clumping together under gravity's pull, shaping galaxies and clusters, while dark energy pushes space itself apart, driving the universe's accelerating expansion. But what if these two invisible forces are secretly communicating? Some theories suggest they could be exchanging energy in ways that subtly alter the cosmos's expansion history, potentially solving some of the lingering mismatches in our observations. Imagine dark matter as sand scattered across a stretch of fabric. The weight of the sand bends the fabric, creating dips where galaxies form. Now picture dark energy as someone tugging at the edges of that fabric, stretching it outward. In standard cosmology, these two actions are independent, but in interacting dark energy models, the sand might be slowly dissolving into the fabric itself, transforming into the very force stretching it. This exchange could mean dark matter isn't constant over time. It might gradually diminish as dark energy grows stronger, subtly tweaking how fast the universe expands at different epochs. The implications are staggering. If dark energy is siphoning energy from dark matter, it could explain why the universe's acceleration kicked in when it did around 5 billion years ago, just as dark matter's density dropped enough for dark energy to dominate. Some simulations even suggest this interaction could smooth out the Hubble tension, that nagging discrepancy between local and early universe expansion rates. Instead of a single, unchanging dark energy, we might be dealing with a dynamic interplay, where the balance between these forces evolves over cosmic time. But testing this idea is like trying to eavesdrop on a conversation in a soundproof room. Dark matter and dark energy reveal themselves only through their gravitational fingerprints. No light, no direct signals, just their push and pull on the visible universe. The best clues might come from comparing how galaxy clusters evolve across different eras. If dark energy is indeed stealing strength from dark matter, clusters in the early universe should form differently than predicted, their growth stunted by the gradual draining of their gravitational scaffolding. Yet every potential signature is buried under layers of cosmic noise. Current telescopes lack the precision to spot these subtle effects definitively, and alternative explanations, like modified gravity or hidden particles, could mimic the same patterns. Upcoming projects like the Vera Rubin Observatory and the Euclid Space Telescope aim to map the cosmos in unprecedented detail, searching for telltale distortions in the distribution of galaxies or the bending of light around massive structures. If they find anomalies that align with interaction models, it would rewrite not just our understanding of dark energy and dark matter, but the entire narrative of cosmic evolution. The possibility of these two shadowy components influencing each other is more than a theoretical curiosity. It's a reminder that the universe's greatest mysteries might not exist in isolation. They could be intertwined in ways we're only beginning to imagine. Until we catch them in the act, though, their conversation remains one of cosmology's most tantalizing unsolved dialogues. What if the universe isn't expanding at all, but we're just seeing it wrong? This radical idea flips mainstream cosmology on its head, suggesting that redshift and galactic motion might not point to stretching space, but to something far stranger happening right under our noses. At the heart of this debate is a simple yet profound question: are we misinterpreting the cosmos because we're stuck in a skewed perspective, like sailors mistaking the horizon's curve for the edge of the world? One alternative to dark energy and expanding space comes from modified Newtonian dynamics, or MIND. This theory argues that gravity behaves differently on cosmic scales than Einstein's equations predict. No dark energy required. Imagine driving a car that inexplicably speeds up when you take your foot off the gas. Standard physics would assume an invisible force is pushing it, but MIND suggests the engine itself works differently at high speeds. In cosmic terms, galaxies at the universe's edges appear to accelerate not because space is expanding, but because gravity weakens more slowly over vast distances than we thought. Critics dismiss MIND as a patchwork fix, pointing out that it struggles to explain the cosmic microwave background or the large-scale structure of the universe without awkward adjustments. Yet its supporters highlight uncanny successes, like accurately predicting galaxy rotation curves without invoking dark matter. The debate grows even thornier when you consider tired light theories, or the idea that our local galactic neighborhood might be sinking into a gravitational well, distorting our measurements like a funhouse mirror. These possibilities don't just challenge dark energy, they question whether expansion is even real, or just a grand illusion born from our limited vantage point. Then there's the holographic principle, which reimagines the universe as a projection of information encoded on a distant boundary. In this wild scenario, redshift and apparent expansion could be artifacts of how that information gets rendered to us, like pixels stretching on a screen rather than space itself growing. It's a stretch, but it underscores how deeply our assumptions about reality might color what we see. The stakes couldn't be higher. If expansion is an illusion, it would mean dark energy, accelerating universes, and even the Big Bang itself might need rethinking. But if these alternatives fail, they still serve a vital purpose, reminding us that science advances by questioning the obvious. After all, every paradigm shift in history began with someone daring to ask, what if we've been wrong all along? Black holes are often seen as cosmic vacuum cleaners, swallowing everything that ventures too close. But what if these gravitational monsters are also playing a hidden role in how the universe expands? Supermassive black holes, lurking at the hearts of galaxies, aren't just passive traps, they're dynamic engines, spewing out energy in the form of jets and radiation as they devour surrounding matter. This torrent of energy might be powerful enough to counteract the stretching of space itself on local scales, creating bubbles where expansion slows or even stalls. Picture a black hole like a cosmic blowtorch, heating up the gas and dust around it so intensely that it pushes back against dark energy's relentless pull. In these regions, gravity and radiation form a temporary alliance, holding space together tighter than the universe at large. Some simulations suggest this effect could be significant, especially in dense galaxy clusters where supermassive black holes feed voraciously. Over billions of years, these localized battles between expansion and black hole energy might subtly skew our measurements of how fast the universe is growing, potentially contributing to the Hubble tension, that nagging mismatch between expansion rates measured nearby versus in the distant cosmos. But here's the twist: black holes might not just resist expansion, they could also fuel it. A controversial theory suggests that as black holes evaporate over unimaginable timescales, they release energy back into the cosmos, effectively acting as dark energy factories. It's a cosmic recycling program where matter falls in, gets compressed to its limits, and then slowly leaks out as pure energy, adding to the universe's accelerating push. If true, this would mean black holes aren't just bystanders in the expansion story, they're active participants, shaping the fate of the universe from within their event horizons. The challenge is untangling these effects from the noise. Black holes are messy eaters, and their outbursts can mimic or mask other cosmic phenomena. New telescopes like the upcoming LISA Gravitational Wave Observatory could shed light on how black holes interact with their surroundings, revealing whether their energy truly leaves a fingerprint on the expansion rate. Until then, these enigmatic objects remain wild cards in the cosmic deck, entities that might hold the key to understanding why the universe stretches the way it does, and whether the forces we think we know are hiding secrets darker than the holes themselves. What if the universe's expansion isn't the beginning of the end, but just another turn in an endless cosmic cycle? This mind-bending idea, known as conformal cyclic cosmology, flips the script on everything we think we know about dark energy and acceleration. Instead of a one-way journey toward heat death or a big rip, the universe might be caught in an eternal loop, where each Big Bang is actually a rebirth from the ashes of a previous epoch. Picture a phoenix made of spacetime, endlessly collapsing and exploding anew, with expansion merely the latest phase in a saga without beginning or end. At the heart of this theory lies a radical reimagining of infinity. Nobel laureate Roger Penrose proposed that when our universe expands to near nothingness, its galaxies evaporated, black holes dissolved, and particles stretched to ghostly thinness, it somehow resets. The dying embers of one cycle become the seeds of the next, with all information scrubbed away except for subtle imprints hinting at past universes. These echoes, called Hawking points, might even be hiding in the cosmic microwave background, faint scars from collisions with long-vanished black holes in prior cycles. But how could this explain today's accelerating expansion? In bouncing models, dark energy isn't a mysterious force, it's the universe gathering momentum for the next rebound, like a cosmic slingshot stretching to its limit before snapping back. Some versions suggest that what we call dark energy is actually the residue of quantum fields left over from the previous cycle, a lingering tension in spacetime that's priming the cosmos for its next collapse and rebirth. Instead of fighting gravity, this energy might be part of a grander rhythm, tuning the universe's expansion to set the stage for the next Big Bang. Critics argue these models stretch physics beyond breaking point, requiring exotic mechanisms to smoothly bridge one cycle to the next without violating energy conservation or entropy. Yet supporters counter that cyclic cosmology solves puzzles standard theories can't touch, like why the universe began in such an improbably low entropy state. If each cycle resets entropy through some unknown process, it would mean our finely tuned cosmos isn't a fluke, it's just the latest iteration in an infinite series. The most tantalizing clue might lie in the sky. If conformal cycles are real, colliding supermassive black holes from past universes could have left faint, circular patterns in the microwave background. While no definitive evidence has emerged yet, upcoming gravitational wave detectors might spot anomalies suggestive of pre-Big Bang events. Until then, the idea of a cyclic universe remains a thrilling what-if, one that challenges us to rethink not just where the cosmos is going, but where it's been. Measuring the universe's expansion should be straightforward. Pick a cosmic yardstick, do the math, and voila. But when scientists use different tools to calculate the Hubble constant, the rate of cosmic expansion, they keep getting different answers. It's like trying to measure a room with a ruler, a tape measure, and a laser, only for each tool to give a slightly different result. This isn't just a rounding error, it's a full-blown mystery, and the culprit might lie in the very methods we trust to map the cosmos. Take Cepheid variables, the pulsating stars that act as cosmic lighthouses. By measuring their brightness fluctuations, astronomers can gauge distances to nearby galaxies. But here's the wrinkle: dust, interstellar particles can obscure these stars, making them appear dimmer and thus farther away than they really are. Even worse, Cepheids in crowded galactic cores can blend with neighboring stars, skewing measurements like a smudged lens. The result, a Hubble constant that might be slightly off, just enough to fuel the tension between local and early universe measurements. Then there's the tip of the red giant branch, another stellar yardstick. When aging stars reach a specific evolutionary phase, they all shine at roughly the same intrinsic brightness. In theory, this makes them perfect standard candles. But reality is messier. Metallicity, the amount of heavy elements in a star, can subtly alter its brightness, like a light bulb flickering based on the voltage. If red giants in different galaxies have varying compositions, their distances could be miscalculated, quietly distorting the expansion rate we derive from them. Gravitational lensing, meanwhile, offers a completely different approach. When massive objects bend light from distant quasars, creating multiple images, the time delays between those images can reveal the universe's expansion speed. But this method depends on modeling the lensing galaxy's mass distribution, a cosmic guessing game where even tiny errors in the map can throw off the timing. Imagine trying to predict a train's speed by watching its reflection in a funhouse mirror. The distortions matter. The deeper issue, each method peels back a different layer of cosmic history. Cepheids and red giants reflect the relatively recent universe, while lensing and the cosmic microwave background probe ancient epochs. If the Hubble constant truly varies across time, it could mean dark energy isn't constant, or that we're missing a fundamental piece of the puzzle. Until we untangle these systematic knots, the Hubble tension won't just be a discrepancy, it'll be a flashing sign that our cosmic rulers might need recalibration. Gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, these are the four fundamental forces that rule our universe. They govern everything from the orbits of planets to the fusion in stars and the decay of atoms. But what if there's a fifth player in the game, one we haven't discovered yet? Some scientists suspect that an entirely new force might be lurking in the cosmic shadows, subtly tweaking the expansion of space itself. It's a wild idea, but if true, it could rewrite the rules of physics as we know them. The first clue lies in dark energy's strange behavior. The cosmological constant, Einstein's simplest explanation for dark energy, suggests an unchanging force woven into space. But what if that force isn't constant at all? Some theories propose a fifth force that varies over time or distance, interacting with matter in ways we've never detected. Picture this: a hidden force that only kicks in on cosmic scales, too weak to notice in a lab but strong enough to push galaxies apart. Unlike gravity, which pulls everything together, this force could act like cosmic anti-gravity, repulsive, pervasive, and invisible. One compelling version of this idea comes from chameleon theories, where the fifth force hides in dense environments like Earth or stars, effectively camouflaging itself. In empty space, however, it could emerge in full strength, mimicking dark energy's accelerating effect. Imagine a chameleon sitting on a leaf. It blends in perfectly when surrounded by foliage, but place it on a blank wall, and its true colors show. Similarly, this force might only reveal itself in the vast emptiness between galaxies, where its push overpowers gravity. Then there's symmetrons, hypothetical fields that change their properties based on the density of matter around them. In crowded regions like galaxy clusters, symmetrons could stay dormant, but in the cosmic voids where matter is sparse, they might switch on, generating a repulsive force that drives expansion. It's like a pressure-sensitive floor. Step lightly, and nothing happens, but remove the weight, and hidden mechanisms activate. If symmetrons exist, they could explain why dark energy's effects seem so uniform yet so elusive. Critics argue that inventing a fifth force is just swapping one mystery for another. After all, we have no direct evidence, just mathematical hints that our current framework might be incomplete. But supporters counter that history is full of forces we once missed, from magnetism to nuclear interactions. When Uranus's orbit didn't match predictions in the 19th century, astronomers didn't throw out Newton's laws, they looked for Neptune. Could dark energy be our modern-day Neptune, pointing to something entirely new? The hunt for this phantom force is already underway. Precision experiments with ultra-cold atoms and torsion balances, devices that measure unimaginably tiny twists, are searching for deviations from known physics. Even the cosmos itself is a lab. Subtle distortions in the cosmic microwave background or anomalies in galaxy clustering might betray the fifth force's fingerprint. If found, it wouldn't just solve the dark energy puzzle, it would open a new chapter in physics, revealing a universe far stranger than we ever imagined. Until then, the question lingers: are we missing a fundamental piece of reality, one that's quietly shaping the fate of everything? Neutrinos are the ghosts of the particle world, shimmering through matter almost untouched, so elusive that trillions pass through your body every second without a single collision. For decades, scientists assumed these particles were massless, zipping through the cosmos at the speed of light, but recent breakthroughs revealed something startling. Neutrinos have mass, tiny but real. And that tiny mass might be quietly shaping the universe's expansion in ways we're only beginning to grasp. Think of the cosmos as a vast, invisible sea filled with these nearly weightless particles. While each neutrino's mass is unfathomably small, a fraction of an electron's, their sheer numbers add up. Estimates suggest there are around 300 neutrinos per cubic centimeter left over from the Big Bang, meaning their collective gravitational pull could subtly influence how galaxies cluster and space stretches. It's like a crowd of feathers, individually weightless, but pile enough together and they'll bend the floor beneath them. This becomes critical when mapping the universe's large-scale structure. Simulations show that neutrinos, with their unique ability to stream freely through matter, act as cosmic smoothing agents. As they zip away from dense regions, they carry energy with them, subtly flattening the peaks and valleys of matter distribution. The result, a universe where galaxies cluster slightly less tightly than they would in a neutrino-free cosmos. This smoothing effect isn't just a detail, it tweaks the very rate at which gravity slows expansion, meaning neutrinos could be quietly skewing our measurements of dark energy's strength. The plot thickens when we consider neutrino flavors. These particles come in three types: electron, muon, and tau, and they can oscillate between them mid-flight. Recent experiments found that their masses aren't equal, hinting at a complex hierarchy that might affect how they interact with cosmic structures. If the heaviest neutrinos are slow enough to get caught in galaxy clusters' gravitational wells, their extra mass could amplify the clustering in ways we haven't fully accounted for. It's like realizing some of those feathers are actually tiny lead weights. Their distribution changes the entire balance, the most tantalizing possibility. Neutrinos might help explain the Hubble tension, if their masses are larger than current estimates, or if they interact in unexpected ways with dark matter. They could reconcile the conflicting expansion rates measured locally versus in the early universe. Imagine a cosmic recipe where you've misjudged one ingredient's quantity. Even a pinch more or less could alter the entire dish. Similarly, neutrinos' hidden influence might be the missing spice that makes all the measurements align. Future telescopes like the Vera Rubin Observatory and the Euclid Space Mission aim to map the universe's structure with unprecedented precision, hunting for neutrino fingerprints in the web of galaxies. Meanwhile, underground detectors like DUNE and Hyper-Kamiok are racing to pin down neutrino masses with higher accuracy. Together they could reveal whether these spectral particles are mere bystanders or silent architects of cosmic expansion. One thing's certain, in the grand puzzle of the universe, even the lightest pieces can tip the scales. What if the universe we see is just one bubble floating in an endless cosmic foam? Eternal inflation, a theory that suggests our universe is one of countless bubble universes, constantly budding off an ever-expanding multiverse, might sound like pure speculation. But startling anomalies in our own cosmos, like the mysterious cold spot in the cosmic microwave background, could be the first tangible hints that we're not alone in the grand scheme of reality. Take that infamous cold spot, a vast region in the CMB where temperatures dip conspicuously lower than surrounding areas. At first glance, it might seem like a random fluctuation. But the odds of such a pronounced cold patch appearing by chance are astronomically low, like rolling a die 1,000 times and getting the same number every single time. Some theorists propose it's a bruise left by a collision with another bubble universe in the distant past. Picture two soap bubbles gently bumping in midair. The boundary where they touch would stretch and distort, leaving a faint imprint. If a neighboring universe grazed ours during inflation, the energy transfer could have left behind a scar in the form of that eerie cold spot we observe today. Then there's the broader unevenness in the CMB's temperature distribution. While the cosmic microwave background is remarkably uniform, subtle deviations from perfect symmetry align suspiciously well with what bubble universes might leave behind. In eternal inflation, each bubble forms with its own unique physical constants and laws, like rooms in a cosmic hotel where every suite has different rules. When these bubbles nucleate and expand, their walls domain boundaries where different physics meet, could create gravitational shadows or pressure waves that ripple into adjacent universes. Our CMB's anomalies might be the faint echoes of those distant borders, whispers from realms where gravity is stronger, light is slower, or even time flows backward. Critics argue these anomalies could have simpler explanations, like instrumental noise or foreground galactic dust, But supporters of the multiverse hypothesis point to another clue: the universe's curiously low entropy at the Big Bang. The fact that our cosmos began in such an improbably ordered state makes more sense if it was born from a higher energy parent universe, inheriting some of that structure. Think of it like freezing ice cubes. Water molecules align into neat crystalline patterns not by chance, but because they're influenced by the colder environment around them. Similarly, our universe's fine-tuned initial conditions might reflect the physics of a broader multiverse, mold, shaping its birth, the most tantalizing possibility. If bubble universes exist, their gravitational tugs could subtly warp the expansion rate in different regions of our cosmos. We already see puzzling variations in the Hubble constant depending on where and how we measure it. Could some of that scatter come from neighboring universes gently pulling on ours like invisible magnets? Future telescopes like the Simons Observatory will map the CMB with even finer resolution, hunting for patterns that no single universe model can explain. If they find them, the cold spot might go down in history not as a curiosity, but as our first glimpse into an infinite ocean of realities, each with its own version of space, time, and the forces that govern them. Until then, the multiverse remains just out of reach, a shadow in the data daring us to look deeper. Einstein taught us that time isn't absolute, it stretches and warps depending on gravity and motion. A clock on a speeding rocket ticks slower than one on Earth, and an astronaut near a black hole ages differently than someone in empty space. But what if this familiar quirk of relativity is secretly warping how we measure the universe's expansion? When we peer at distant galaxies billions of light years away, we're not just looking across space, we're peering back in time through layers of warped spacetime, where the very fabric of reality might be playing tricks on our observations. Take a galaxy racing away from us at near light speed due to cosmic expansion. According to relativity, time for that galaxy would appear to crawl from our perspective, like watching a movie in slow motion. This means the light we receive isn't just redshifted from the stretching of space. The emissions themselves could be artificially stretched over time, making the galaxy seem to recede faster than it truly is. Imagine shouting across a canyon while the wind carries your voice away. Not only does the sound fade, but your words might reach the other side unnaturally drawn out, creating the illusion of slower speech. Similarly, time dilation could exaggerate the apparent speed of distant galaxies, subtly skewing our calculations of how fast the universe is growing. The challenge: untangling these effects from pure cosmological expansion. When astronomers measure redshift, they assume it's solely due to space stretching, but if time dilation adds an extra layer of distortion, our cosmic yardstick could be bent without us realizing. Some studies suggest this might contribute to the Hubble tension, that nagging mismatch between expansion rates measured nearby versus in the early universe. If galaxies 7 billion light-years away are subject to stronger time dilation than we've accounted for, their redshifts might encode a double deception: space expanding plus time bending. But here's where it gets thorny. While special relativity's time dilation is well tested in labs and near-Earth environments, applying it across cosmic distances introduces wildcards. Gravitational lensing from invisible dark matter clumps could further twist spacetime along our line of sight, adding noise to the signal. Even the motion of our own Milky Way, barreling through space at over 1 million miles per hour, might create a subtle time parallax effect, where galaxies in one direction appear slightly more time dilated than those in another. The most radical possibility, that time itself flowed differently in the early universe. Quantum gravity theories suggest spacetime near the Big Bang might have been frothy and unstable, with time fluctuating like choppy water before smoothing into today's steady stream. If so, light from that era could carry imprints of primordial time warping, masquerading as extra redshift in our measurements. Future gravitational wave observatories might detect these echoes in the ripples of colliding black holes, offering clues about whether ancient time behaved differently. Until then, the question lingers: are we measuring the universe's expansion, or just witnessing time's elastic nature on the grandest scale? What if the universe isn't just expanding but sitting on a cosmic knife's edge, one quantum tick away from unraveling completely? The concept of vacuum decay paints exactly that nightmare scenario. Our entire reality might exist in a false vacuum, a temporary high-energy state that could collapse without warning into a more stable, lower-energy configuration. Think of it like a ball perched at the top of a hill. It seems stable for now, but the slightest nudge could send it tumbling into the valley below, rewriting the rules of physics in an instant. This isn't just theoretical doom-mongering. In quantum field theory, the vacuum isn't empty, it's a seething soup of potential energy that defines the very laws of nature. If our vacuum is metastable, a random quantum fluctuation could trigger a bubble of true vacuum to form somewhere in space. Like an ink drop spreading through water, this bubble would expand at the speed of light, its boundary rewriting physics as it passes. Inside this new region, fundamental constants might change, gravity could strengthen, atoms might disintegrate, and the fabric of spacetime itself could reconfigure. The expansion of the universe wouldn't just accelerate, it could snap into an entirely new regime overnight, governed by rules we can't begin to predict. The most unsettling part: we might never see it coming. If vacuum decay occurs even 100 light-years away, the bubble's edge would reach us at light speed, giving no warning before it obliterates our understanding of reality. Stars wouldn't just redshift, they'd wink out of existence as their atomic structures fail. Dark energy's push could reverse, intensify, or morph into something unrecognizable. It's the ultimate cosmic reset button, and we'd have no way to press pause. Yet here's the twist: vacuum decay might have already happened elsewhere. Some theories suggest our universe's accelerating expansion could be the aftermath of an ancient decay event, a phase transition that altered dark energy's strength billions of years ago. Others speculate these bubbles constantly form in the quantum foam but fizzle out before they gain traction, like popping soap bubbles in a bathtub. The Large Hadron Collider has searched for hints of vacuum instability by measuring the Higgs boson's mass, which suggests our vacuum might be just barely stable, or already teetering toward collapse. The real enigma: if vacuum decay occurs, would it halt expansion, supercharge it, or replace it with something even stranger? Some models predict a new vacuum state could freeze spacetime into crystalline rigidity, halting all motion. Others imagine a runaway Big Slurp where expansion becomes infinite, shredding the cosmos atom by atom. Until we understand the true nature of the vacuum, these possibilities remain terrifyingly open, a reminder that the universe's expansion might not just be a gentle drift, but a countdown to a rewrite we can't yet fathom. Entropy isn't just about disorder, it might be the hidden engine behind the universe's accelerating expansion. The second law of thermodynamics tells us that entropy, the measure of randomness in a system, always increases over time. But here's the twist: what if that relentless march toward chaos isn't just a byproduct of cosmic expansion, but the very thing driving it? Picture the universe as a cosmic battery running down. Every time a star dies or a black hole evaporates, energy disperses, and entropy climbs. Some theorists argue this growing entropy could generate a kind of pressure, an outward push that counteracts gravity's pull. It's like blowing up a balloon while the air inside grows hotter and more chaotic, except instead of air, it's the sheer randomness of the cosmos itself exerting the force. The more the universe expands, the more entropy increases, creating a feedback loop that could explain dark energy's mysterious push. This idea gets wilder with entropic gravity, a radical hypothesis that flips our understanding of gravity on its head. Proposed by physicist Eric Verland, it suggests gravity might not be a fundamental force at all but an emergent effect of entropy, a sort of cosmic illusion created by the universe's tendency toward disorder. Imagine walking through a crowd. People naturally shift to let you pass, not because of some invisible force, but because it's the path of least resistance. Similarly, entropic gravity posits that what we perceive as gravity could just be space-time rearranging itself to maximize entropy. If true, this could mean the accelerating expansion isn't caused by dark energy, but by the universe's innate drive toward chaos. Critics argue this is a stretch. For one, entropic gravity struggles to explain precise observations like the orbits of planets or the bending of light around galaxies without reintroducing traditional gravity through the back door. And while entropy certainly increases as the universe expands, pinning acceleration directly to it requires some speculative leaps, but supporters counter that standard cosmology has its own gaps, like the unexplained weakness of dark energy, and that entropic theories might fill them in unexpected ways. The stakes are high. If entropy is secretly fueling cosmic acceleration, it would mean the universe isn't just expanding, it's unraveling on a fundamental level. Stars, galaxies, even the fabric of spacetime itself could be caught in a slow-motion dissolution, with entropy as the silent conductor. Future experiments like measuring subtle deviations in gravitational waves or probing the quantum structure of spacetime might reveal whether this provocative idea holds water. Until then, entropy remains a tantalizing wild card, a reminder that the universe's greatest mysteries might not lie in the forces we know, but in the chaos we're only beginning to understand. When we measure the universe's expansion, we're not seeing the full picture, just the parts illuminated enough to catch our attention. Think of it like trying to gauge a city's population by only counting people under streetlights at night. Brighter galaxies dominate our surveys, while dimmer ones slip through the cracks, potentially skewing our cosmic senses in ways we don't yet understand. This observational bias could be quietly distorting the Hubble constant, making the universe's expansion seem faster or slower than it truly is. Take supernova, the brilliant stellar explosions we use as cosmic mile markers. Type Ia supernovae are especially valuable because they blaze with consistent brightness, allowing astronomers to calculate their distances with precision. But here's the catch: these supernovae are easier to spot in younger, metal-rich galaxies, which tend to cluster in denser regions of space. If we're disproportionately measuring expansion rates in these crowded neighborhoods, we might be missing how the universe behaves in its quieter, emptier stretches. It's like judging global weather patterns by only monitoring tropical storms. You'd miss the subtle shifts in deserts or polar regions that could change the whole story. Then there's the Malmquist bias, a statistical gremlin that creeps into nearly every astronomical survey. Simply put, brighter objects are visible at greater distances, meaning our telescopes naturally favor the most luminous galaxies in any given sample. Over vast cosmic distances, this can warp our perception of how galaxies are distributed and, by extension, how fast they are moving apart. Imagine trying to study bird migration by only tracking the loudest flocks. You might conclude all birds travel in deafening groups, missing the silent solo flyers that could append your assumptions. Even the tools we use introduce their own distortions. Ground-based telescopes struggle with atmospheric interference, while space telescopes like Hubble or JWST have limited fields of view. Some regions of the sky get scrutinized in exquisite detail, while others remain blurry or unexplored. These inconsistencies could mean we're stitching together a patchwork map of the cosmos, with some areas artificially sharpened and others smoothed over. Future missions like the Vera Rubin Observatory aim to fix this by scanning the entire visible sky in unprecedented detail, but for now, our view remains fragmented. The most insidious bias might be our own cosmic address. We're stuck in a single vantage point, like ants trying to map a forest from one tree. Nearby galaxy motions are tangled up in the gravitational dance of the local group. while distant galaxies' light reaches us through layers of warped spacetime. If our neighborhood is atypically dense or sparse, our local measurements of expansion could be wildly unrepresentative. It's the astronomical equivalent of polling voters in a single county and assuming the whole country feels the same. Until we untangle these biases, the true rate of cosmic expansion will remain elusive, but here's the hopeful part: every identified bias is a chance to refine our tools and sharpen our vision. The universe isn't hiding its secrets, it's just waiting for us to ask the right questions. The mysteries of cosmic expansion might finally meet their match not in a single eureka moment, but in the razor-sharp gaze of a new generation of telescopes and space missions. At the forefront is the James Webb Space Telescope, already rewriting the rules of astrophysics with its infrared vision. Unlike Hubble, which peered through cosmic fog with visible and ultraviolet light, Webb slices through dust clouds to study the earliest galaxies, hunting for clues about how dark energy's influence has evolved over billions of years. Its observations of ancient supernovae could reveal whether dark energy's push has changed over time, or if it's been a steady, relentless force all along. Then there's the Vera Rubin Observatory, poised to revolutionize our cosmic census. Perched in Chile's arid mountains, its massive mirror will scan the entire southern sky every few nights, capturing the faint glow of billions of galaxies. This isn't just a snapshot, it's a time-lapse of the universe's expansion, tracking how galaxy clusters warp and shift over a decade. By mapping the subtle distortions in their shapes caused by dark matter's gravitational lensing, Rubin could uncover whether dark energy's strength varies across space, or if hidden cosmic structures are warping our measurements. The Euclid Space Telescope, launched by the European Space Agency, takes a different approach. Designed to create the most precise 3D map of the universe ever made, Euclid will measure the exact positions of over 1 billion galaxies, tracing how their distribution has stretched and clumped under dark energy's influence. Its secret weapon, two instruments working in tandem, one to capture galaxy shapes for lensing studies, another to measure redshifts with staggering accuracy. If dark energy interacts with dark matter or gravity behaves oddly at cosmic scales, Euclid's data might catch the discrepancy red-handed. NASA Nancy Grace Roman Space Telescope, set to launch later this decade, could settle the Hubble tension once and for all. Dubbed the Dark Energy Detective, Roman will study Type Ia supernova with Hubble-like precision, but across a far wider swath of the cosmos. More crucially, it'll peer into the infrared spectrum, where light from the universe's early expansion phases hides. By comparing these ancient supernovae to nearby ones, Roman might reveal whether measurement errors or new physics are to blame for the conflicting expansion rates. But the real game-changer could come from the ground. The Square Kilometre Array, a sprawling radio telescope network across 2 continents, will detect hydrogen emissions from galaxies so distant their light has traveled for over 10 billion years. Hydrogen's signature wavelength acts like a cosmic ruler stretched by expansion. It tells us exactly how fast space was growing at different epochs. Unlike optical telescopes, SKA isn't fooled by interstellar dust, offering a crystal-clear view of the universe's adolescence. These missions share one audacious goal: to turn speculation into certainty, whether confirming if dark energy evolves, exposing hidden dimensions, or revealing flaws in Einstein's gravity. Each tool brings us closer to answers, or perhaps to deeper questions we haven't even thought to ask yet. The universe's greatest secrets won't surrender easily, but for the first time in history, we've built the keys to unlock them. We've journeyed through 25 of the universe's most tantalizing expansion mysteries, from the enigma of dark energy's origins to the unsettling possibility of vacuum decay, from cosmic voids warping spacetime to the deafening silence of those missing gravitational waves. Each question isn't just a gap in our knowledge, it's a frontier, a shimmering edge where the known cosmos frays into the unknown. The Hubble tension, the phantom pull of extra dimensions, the eerie alignment of the axis of evil, these aren't mere puzzles. They're invitations, cosmic breadcrumbs leading us toward a deeper understanding of reality itself. What makes these mysteries so electrifying isn't just their scale, it's what they reveal about our place in the grand scheme. Every discrepancy in our measurements, every anomaly in the data, whispers the same truth: the universe refuses to fit neatly into our models. It's messier, wilder, and far more wondrous than we've dared to imagine. And that's the heart of science, not just collecting answers, but learning how to ask better questions. So here's the takeaway: the universe's expansion isn't just a fact. It's an ongoing conversation, a story still being written, and you're part of it. Maybe your favorite mystery is the Big Rip's apocalyptic edge, or perhaps you're captivated by the quantum flutter of vacuum energy. Whatever it is, drop it in the comments. Let's geek out over the cosmos together. And if you're hungry for more deep dives into space's greatest secrets, hit subscribe. Because the next revelation, it's already out there, waiting in the dark.